Okay, so 6.5 notes. What we're going to focus on in this section is finding the center of mass, and we're actually going to see how we can use calculus to help us find the center of mass for both uniform and non-uniform objects. So again, this section actually is a big section to make sure you're paying attention to. And the reason we're doing this now is it actually comes back in for chapter 7 when we talk about the moments of inertia for various shapes. So a lot of the same skills we're going to see here pop up again later on as I do that in chapter 7. So again, make sure you're following along. If you have any questions, let me know. But let's start by reviewing, right, how do we find the center of mass in general for the system? So if I asked you to find the center of mass, well, to find the center of mass, we would take each mass, right, if we were doing this with a whole bunch of discrete objects, we would take each of these individual masses, right, and multiply them by their specific positions and add them all up, right, and so on and so forth. And then I would divide them by the total mass of the system, right, so m1 plus m2 plus m3, and again on so on and so forth, right. A lot of times we'd refer to the denominator there as just the total mass of the system. So we might choose to call that just a capital M from time to time. And you guys will see as I use that later on once I do some calculus. Right. This is more of a side note, but a good thing to review while we're talking about it anyway. Right. So how did we find the velocity of the center of mass? Right. Well, the reason I bring that up is pretty much the exact same calculation. Right. The velocity of the center of mass is mass 1 times its velocity plus mass 2 times its velocity. That should be v2. This should have been x2 up here. And then mass 3 times its velocity, and again so on and so forth. Right? So divided by the total mass of the system. The significant part here, which again is actually more of a momentum connection than it is for this section. But if you look at the numerator represents the total momentum of the system. So we know that before and after any collision, momentum is conserved as long as there's no outside force. Right, so the velocity of the center of mass is actually equal before and after a collision, and that's something that again is a side note for this chapter here, but it's something worth reviewing, and it is a concept worth making sure you're pretty comfortable with. But anyway, we are going to focus on for today on the position for the center of mass. Right, we're going to look at finding that position, and so the question becomes, how can we use calculus to help us find the center of mass? Well, again, ideally, if I was doing this, right, if I gave you a uniform rod, or if I gave you an object that had some mass to it, so let's say I give you a uniform rod. If I was algebraically trying to find the center of mass of that system, I would have to algebraically add up the mass of each individual particle, right, and then divide each mass times position divided by the total mass of the system. So in other words, what I'm saying is I would do mass 1 times position 1 plus mass 2 times position 2, all the way up into, right, mass essentially infinity, right, so I'll call it mass I, right, whatever the final mass in this, so in the hundreds of millions probably. But anyway, times the final position, I would add all those up, and then I would divide it by the total mass of the system, which I know would just be M, it'd be the mass of the rod, right, so algebraically if I was trying to do this, I would need to multiply each individual particle times its position and then divide by the total mass. Obviously, that means we have some problems, right, algebraically. If there are hundreds of millions, if not even more, right, hundreds of billions of particles in that given rod, how in the world are we going to algebraically add them all up? Well, we're not, right, we're not. But what we are doing is we're finding the summation. So the numerator here is finding the summation of all of my m's, right? So it's finding the summation from mi times xi for every I from, again, from 1 to whatever that number of particles we have, right? So we have the numerator here, which would be, again, that summation, and then divided by the total mass of the system. Well, the significance here is how does this tie into calculus? And you guys have probably reached the point in your calculus course where you've actually seen, right, the summation symbol before. And in fact, the summation symbol comes up in the definition of integration. When you integrate something, what you're really doing is you're finding the sum of all of those individual strips or masses. So kind of graphically again, if you will, right, when you integrate, the first way that you talked about doing it was a Riemann sum, which is when you take all sorts of those little rectangles, right, and you add up the total area of all of those rectangles, and you find from that information then the total area underneath that curve. We're essentially doing the same thing, right, with each mass times its position. We're taking, if you imagine this graphically, we're taking the mass times its position, we're adding all of those up, we're summing all of them up, and then dividing by the total mass of the system to find the average position, right? So again, the key concept here is the numerator is really, by definition, it's the integration of our mass as a function here, right? So that's where this ties in. So taking kind of a side note on that, so when I go from I equals 1 to n of xi mi, what that really translates to then is the integration from 1 to n for my position, right? So it's going from my position function. So again, how this actually translates is it's x times dm, where dm is the change in mass per position. So essentially what we're going to be doing here, and again, this is a concept that pops up a lot throughout the next chapter, but what we're going to do here is we're going to take a whole bunch of these really thin strips, right? So if I could find each of these thin strips, if I could find the mass per strip and then times that position and add all of those up, then divide by the total mass of the system, I would have my average center of mass, right? So this is kind of the key relationship thing. Okay, so that's how calculus ties in, right? That's how we're going to do this. So if I ask you to find the center of mass, the overall equation we're actually working with, the center of mass would be, again, this integration from 1 to whatever my ending parameter is, which we'll look at here in some specific examples, and then x dm divided by the total mass of the system. Another way we often write that would be to pull the mass out, so 1 over m, and then times the integral of 1 to n for x dm. Now I know right now all the variables make it pretty tricky, make it seem maybe a little bit intimidating, but it's actually not that bad as we work through it. I will make a quick side note here. Some of us, I hope most of us at this point have seen the calculus, but we are going to deal a lot with definite integrals in this case. And what a definite integral, so just as an example, right, if I give you the definite integral from 1 to 4 of x squared dx, well, definite integral says we integrate this like we normally would, so integrating this function, I would get x to the third divided by 3. And then these are the parameters that I plug in. So this is kind of my final position, this is my initial position. So those are the parameters, the values that we then plug in for x. So rather than having to worry about the plus c, which we normally do when we integrate, because we're actually going to plug in those parameters of 1 and 4, the c is actually going to be irrelevant, and you guys will see what I mean as I do this. Right, so what I do is I plug in the top parameter there, so 4 cubed over 3. I obviously did not choose very friendly numbers, but that's okay. So I would plug that value in, and then I would subtract the starting parameter. I would subtract that initial limit of the initial position there of the limit. So then I would plug in 1. So 1 cubed over 3 plus c. And here's where obviously the plus c doesn't matter. When I distribute the negative, I have plus c, and then I end up with a minus c, and so obviously the c's end up canceling out. So the final answer of this integral here would be 4/3 over 3, so 64 over 3, minus 1/3 over 3, so 1 over 3, which actually does work out pretty nicely to be 63 over 3, or better yet, 21. And do not answer that, by the way, in the stupid way of answering 21. But anyway, so that's a side note again on definite integrals. We will see that a lot, though, in this section. Okay, so key concept. If I want to find the center of mass, the position of the center of mass, the way that I do that is by finding the integral of the position times the mass, or times the change in mass, divided by the total mass of the system. Okay, so let's look at what this actually looks like through a few examples. Okay, so example number 1 here says, show using calculus, so show using the means we just defined, that the center of mass for a rod of mass m and length L lies midway between its ends, assuming the mass has a uniform mass per unit length. So again, the definition I want us to be thinking here is the definition of the center of mass is 1 over the total mass of the rod, which they defined here as capital M, and then from the parameters from my initial position to my final position, which we'll consider here in just a second, and then times x times dm, or of x dm. Right, so let's talk briefly then about our parameters. Right, well, if I'm defining this as a rod, so again it's a rod of length L, just like we always do when we find the center of mass, you just need to choose kind of an arbitrary starting point. And so what I mean by that is, what I'm going to do is just choose either the left or the right hand end. So I'm going to choose this to be 0, which would mean the other end of my rod, right, would be a distance of L. So in this case, I'm going to go from 0 as my first position to the final position of L, right? And I'm going to find the sum of all of these masses along the way. Right, so that's the goal. That's what we're going to look at doing here. So then the question is, right, how does this work? Because if I try to integrate it, right now the problem is I'm trying to integrate x with respect to dm, and that obviously doesn't really fly. And so this is where the trick to these questions comes in. Right, this is where the trick to these questions come in. When you think of dm, I want you to think of that as the mass per area or the mass per strip. Right, so think of that as the mass per segment, if you will. And maybe that's the best way to think about it. So it's the mass per segment. So again, what we're doing kind of conceptually with this rod, we're taking that rod and we're cutting it up into a whole bunch of these infinitely thin strips, right? And the dm represents, again, the mass per each of those strips, right? So how would I find the mass per that strip, right? What would I have to do to find the mass per strip? Well, there's a couple things that come into play. One is the fact that it has uniform mass per length density, right? So a lot of times they'll use a lambda to represent that. But what that tells me is the mass is evenly distributed. So if I have a total mass of m, then it's going to be evenly distributed divided by that total distance of L, right? So this would represent again, the mass per length of the rod, right? So if I told you then if this mass per length was 24 divided by 10, then if I knew how wide each of those strips was, I would just take this mass per length times the length of each of those strips, and that would give me the mass per strip, right? And that's the key. So dm then, again, is going to be the mass per length times the width of each of those strips. Well, how wide is each of those strips? Well, the width of each of those strips is going to be whatever I'm choosing to be my delta x, my change in x, right? So the width of each one of those strips is going to be, in other words, x, right? That's how wide it is. So what this ends up looking like then for me is dm equals the mass per length of the rod times x, times whatever that change in position is, whatever that position is, right? So that's how this kind of comes all together. So again, and this is the tricky part. By all means, if you guys have trouble with this, come find me so I can help clarify. I don't expect this to be necessarily easy to follow the first time through. But we do want to think of the dm here again as the amount of mass per strip, or per segment, and then again, the way that we find that is we find the mass per length and then multiply it by that length, by that change in length for the width there. Right, so then bringing this all together, right, I bring this back to my integration here. It'd be 1 over m from 0 to L, and then of x times, instead of dm, I'm going to replace that with mass per length times x, and then I should say that this is actually, dx, not x. Right, so that's actually a dx because it is the change in length. So sorry about that. That's not actually the x, that's the change in x. So dx. Right, so anyway, what this ends up looking like as I integrate this, right, is 1 over m from 0 to L. I can go ahead and pull the m and the L out front. So I'm going to multiply that out front over here, which obviously works out very nicely because, hey, the m's can go ahead and cancel out. And then I just have x dx inside the integration. Right, and it is worth noting that the only reason I can pull out the mass and the length is because both of those are constants, right, for the entire rod. So again, the position, right, the position is, in this case, 1 over L, the integration from 0 to L of x dx. Well, x dx actually works out very nicely to be simply x squared, right, divided by 2. So I get x squared divided by 2 from that integration. And again, this is where the definite integral comes into play. I still have the 1 over L out front, by the way, but as I plug in L here, and as I plug in 0, I'm going to get L squared divided by 2 minus 0 squared divided by 2. And obviously the 0 squared divided by 2 goes away. So what I end up with is the center of mass equals 1 over L times L squared divided by 2. And obviously if I do just a little bit more cleanup here, one of the L's can cancel out. So I get the center of mass equals L over 2. Right, which again in general terms tells me that the center of mass is going to be half of the length of this uniform rod. Okay, so again, cleaning up the one mistake I did make through here, and I want to make sure we do go back, right? The mass per strip there is the mass per length times the change in that displacement, right? The change in x. But otherwise, once we get that set up, it's just doing integration. So anyway, a tough example, like I said, guys, if this is something that you feel lost with, by all means come let me know so I can help you out with it. It is something that's worth noting, and I'll do another example here in the second part of this video. Okay, so stay tuned for that.